Before looking at example 4 about Swiss lottery, let's look at chapter 8.1 using combinatorics more in general, and I suggest that you always try to solve the example by your own and then look at the film. So I'll just explain the examples, but the idea is try it on your own and then watch it. So in example 1, we have a Laplace experiment. All the different delegations have the same probability. So we have to find out how many delegations are possible at all, and then how many delegations to fulfill the criteria. There are 24 choose 5 possibilities to choose 5 persons out of 24. So these are all the possible delegations. To choose 3 girls out of 16, the possibilities are 16 choose 3, and for 2 boys out of 8, there is 8 choose 2 possibilities. And since we can or want to combine any delegation choice of girls with any delegation choice of boys, we have to multiply the two, and so we get for the probability of having a delegation of exactly 3 girls and 2 boys is 37%. The probability that there will be members of both genders, that means that there will be at least one girl and at least one boy, means it is exactly the complement to the probability of that there will be no girls or no boys. So the probability of no girls plus the probability of no boys, which results in 8 choose 5, so choosing only boys divided by 24 choose 5, or 16 choose 5, choosing only girls divided by 24 choose 5. And the final result is approximately 10%. Note that we could have calculated these probabilities also in different ways using trees. So the probability for A, 3 girls and 2 boys, we could just say, okay, what is the probability of getting, when we choose the 5 delegates, one after the other, to get first a girl, then a girl, again a girl, then a boy, and then a boy. And we see that we get this product. We can then look at the different orders of choosing 2 boys and 3 girls. So first the 2 boys and then the 3 girls. And when we look at the 2 things, we see, well, this is the same probability. So the question is again, in how many ways can we choose 3 girls and 2 boys? Well, there are 5 choices to be taken, and we want to find the 3 times where we will choose the girls. So 5 choose 3 times the upper probability. And we get again approximately 37%, obviously the same like before. Now example 2. Again, a Laplace experiment, all arrangements have the same probability. Since there are 7 books, if there are no conditions, there are 7 factorial possibilities to arrange them. If the 3 German books have to stand next to one another, then there are 5 possible places for where to place the first of the 3 German books, the most left one, let's say, namely on places 1 to 5. And then we can arrange the 3 German books in any way we like, and also the 4 places where the English book stands can now be arranged. The books there can be arranged in any possible arrangement, so 4 factorial. For the German books we got 3 factorial, and so we get final result 1 divided by 7. Now let's get to example 3. A full house means that we get 3 times the same number and 2 times the same number. So for example, 3 times a 5 and 2 times a 4. We can assume that the 5 dice are numbered or arranged, or that we're rolling them one after another. So let's say the order in which we get this full house is 5, 5, 5, 4, 4, which means the probability is just 1 divided by 6 multiplied with itself 5 times. So we get 1 divided by 6 to the power of 5. The question is, in how many ways can we get this 5, 5, 5, 4, 4, because it will be the same no matter in which order we get it. Well, the number of possibilities is 5 choose 3, the 3 times where we get the 5, or we could also say 5 choose 2, the 2 times where we get the 4, times the upper probability 1 divided by 6 to the power of 5, which is just 10 times 1 divided by 6 to the power of 5. How many different possible full houses are there? Well, there are 6 possibilities for the number which will occur 3 times, and since this number cannot occur then the other 2 times there are 5 possibilities for the other number, so this means 30. And so we get the probability for getting a full house is 30 times this upper probability here, and this yields in the end approximately 4%. Let's get now to example 4. There are 2 different streets possible when rolling 5 dice, so you can get 1, 2, 3, 4, and 5, or 2, 3, 4, 5, and 6. Again, let us assume that the dice are ordered or numbered, or that we just roll one after the other. And the probability of getting 1, 2, 3, 4, 5 in this order is obviously 1 divided by 6 to the power of 5. The question is, in how many ways can we get this 1, 2, 3, 4, 5 in different orders? Well, there are 5 factorial possibilities, so it's 5 factorial times 1 divided by 6 to the power of 5, which is 120 times 1 divided by 6 to the power of 5. We call this, by the way, this 1, 2, 3, 4, 5 a small street, and 2, 3, 4, 5, 6 is a large street, so the probability of a small street is obviously the same like that of a large street. And to get the probability of a street, we just have to add the 2 probabilities since they are mutually exclusive, and we get in the end approximately 3%. Let us get to the last example, example 5. The probability that Corina hits the hoop in at least 1 out of 4 tries is 1 minus the probability that she does never hit it, which is 1 minus 0.75 to the power of 4, so approximately 68%. Let us now look at the probability of hitting the hoop at least once in n tries, which is obviously the 1 minus the probability of not hitting the hoop in the n tries, which is 1 minus 0.75 to the power of n. And we want this probability now to be 0.9999%. So let's solve this for n. Well, and we have to use the logarithm here. So it's a logarithm in base 0.75 of 0.01. And we get as a result 16.01. And we want the probability to be at least 99%. So this means we have to round this result up. So the correct final solution is n is 17. She needs to plan for 17 tries so that the probability that she will hit at least once is at least 99%. If she planned only for 16 tries, the probability would be minimally smaller than 99%.